Hey guys, so today I'm going to be building a deck from scratch. Basically, what a deck is a double-ended queue. A deck is kind of short for that. And it's a data structure that lets you add and remove elements from both the front and the back. So normally a queue, you can take stuff from the front out and you can add stuff from the back. So it's kind of like an actual queue, but a deck, you can kind of manipulate it from both sides. You would use a deck when you need more flexibility than a normal queue or a stack. And some examples of this would be when you're scheduling tasks, uh, for example, on LeetCode, a sliding window problem, and then to undo or redo systems. So most languages give you a deck for free. It's in some libraries, but that kind of hides how it really works. If you understand how a deck is really implemented, you can understand memory, performance, and why some operations are fast while others are slow. That's why I'm not going to be using a library here, and I'm going to be showing you guys how a deck really works. So I'm going to be building this deck using an array, so let's first define a class. So I'm using Google Colab. So let me see, deck, deck. Yeah, I'm pretty sure that's how you spell it. So you want to define your init first for any class. And our first group is going to be a data, and we'll say it would be an array of 8 with, we start off with no data. Then you want to define the size of it, which you're going to be able to call. And then we also want to define our front pointer. So we can do that. So the key challenge is that arrays have a fixed size, so I need a way to reuse space efficiently and grow when necessary. I'll do this by treating the array kind of like a circle and keeping the pointer and keeping track of a front pointer. So this is an array of size 8. I'll use the size variables to know how many elements are stored. This is going to help us when we want to call things like dot size, and it'll be constant. You can just call that. And this step is critical because a small indexing mistake will break everything. So I'll first start off with the resizing function, which will be basically like that. But we want to define new data, and then it'll be none, and then times new capacity, my bad. And then for I in range, self.size, new data I equals, yep, just like that. So basically what this is saying is, so new data at I will become the self data. So basically this new one will become the self one plus I, and I in this case will be the index for each size. And then you're doing a modulo to divide by the length of the data. So when the array is full, I'll allocate a new array that is twice as large and copy elements over in the correct order, because we want this to keep the indexes. And then at the end, you say self data is equal to new date, new data. And then self.front is equal to 0. So you basically reset everything with, but also keep all the current information. So that's our resize method. Now we want to implement a add first method. So add first, we'll do self and item. So if self dot size is equal to dot data, and then you could do self resize self dot data data times 2, and then Yup. Okay. So before inserting, you want to check if the array is full, which is basically that, and then place the new item and see if you need to resize it, because if it is full, you would need to resize the whole array again. And then you'll move the front pointer to backwards using the modular arithmetic, which is this part. And then after that, you would put the item in the index wherever you want, and then you would, after that, iterate the size by one. So the size is corresponding to how many elements there are. And now, because it's a double-ended queue, we want to have a add last function. So it would be that. So it's basically the same thing, except it'll be adding to the back this time. The front. You would want to keep that. Just like that. And this is basically doing the same thing. You want to compute the index by taking the front pointer plus the current size. So that would be here, and then doing the modulo operation on how long the data is. And that's how you get the index. You substitute it into the item. And yeah, it's basically the same thing. This is constant. This whole method will be constant because you won't really need to resize it. If you do need to resize it, obviously it'll change, but just adding will not change its constant time. So now we want to go to removals. We'll start with remove first, I guess. And then that'll be self. We'll assume that the deck is not empty. And if it is empty, instead of throwing an error, we will just return none. And if it isn't, then self.data self.front. Boom. Let me just make sure that it did that right. Front +1. Okay, yeah. And then we need to make sure that the size is corresponding to that. So minus equals 1. So the size will decrease by 1. And then you'll return the item. I believe that's right. Yep. So removing first, we'll remove the element at the front. It'll clear that slot and then move that front pointer forward and decrease the size by 1. So think of it as it is kind of taking the first part out, and then it'll make the front pointer point to the next block of data. The core idea is that the array is treated like a circle. The modulo operation is what makes it all possible. This is why array-based decks are fast and widely used. Now we'll go on to removing last. So for removing last, this will be easier than the removing first. It will add the same condition. If the size is equal to 0, we'll return none. Then index will be equal to exactly that, and then item will be equal to self-data.index. Yep, exactly like that. But in this case, the pointer does not need to be changed. So the remove first and remove last are pretty similar, except the front pointer in this case will not be changed because you aren't removing the front. the quote unquote front, rather you are removing the last. So if you understand this implementation of how a deck is really used, it'll help you with stacks, queues, and linked lists. It'll help you understand it a lot better. It'll be a lot easier. So this is the kind of knowledge that actually shows that you can understand new and different data structures and not just how to use them. Knowing how to use them will help, but understanding how to code this will help you understand things like how long runtime will be, things of that nature, and different use cases. I hope this tutorial helped you.